going to discuss about the energy band diagram and the breakdown in the PN junction diode. So in this energy band diagram, the region in the left side of the p-type with the accepted density, we denoted that as Na, while the region on the right side is denoted as Nd, since it is a donor density. And here the dopants are assumed to be swallow, so that electron density and the hole density is approximately equal, and there exists an energy gap which we take it as the energy band diagram. So here you can see the drift as well as the diffusion current for the both the N-type and the P-type material. So there exists some energy gap in between the N-type and the P-type, which we call it as the energy band. So to reach the thermal equilibrium, these electrons will close to the metallurgical junction and they diffuse across the junction in the p-type and the n-type region. And also this process will leave the ionized donors behind, creating a region around the junction which is depleted of mobile carriers. When this charge due to the ionized donors and the acceptors cause an electric field, therefore there will be change in the electric field, that is, it flows in the opposite direction. The diffusion in the carriers also continues until the drift current balances the diffusion current, thus by reaching the thermal equilibrium as indicated by the constant Fermi energy. While in the case of the thermal equilibrium, when there is no voltage is applied between this N-type and the P-type material, there will be an internal potential which is caused by the work function difference between the N-type and the P-type semiconductors. So this can be seen in the diagram. So you can see when the energy that is when the acceptors flows through the donor material, there will be a decrease in their bias, as well as when it comes from the donor to acceptor, there will be decreased. So when the increase in the voltage, when it goes to the minority carriers, there will be some changes in the electric field. So with an applied bias voltage, a forward bias corresponds to the applied positive voltage and related to this cathode. When the reverse bias corresponds to the negative voltage, this voltage is proportional to the difference between the Fermi energy in the N-type as well as the P-type regions. So as the negative voltage is applied, the potential across the semiconductor increases and there creates the depletion layer width. As the positive voltage is applied, the potential across the semiconductor decreases and with it the depletion layer width. So the total potential across the semiconductor equals the built-in potential minus the applied voltage. Breakdown in the PN junctions. So when a PN junction is reverse biased, it allows very small current to flow through it, and the current is due to the movement of the minority charge carriers. So if any reverse bias is made too high, the current through the PN junction increases abruptly and the voltage at which the phenomena we call that as breakdown voltage. When there is a change in the voltage, that is when you are increasing the voltage highly, to some instances there it will be increasing, and at a particular voltage it loses its energy and goes to the reverse bias and it starts increasing at the negative side. So at this breakdown voltage, the crystal surface breaks down. Sometimes overheating may also occurs, which may affect the crystal. So these type of the process can be caused by the junction breakdown. So one is Zener breakdown and another one is avalanche breakdown. In the case of avalanche breakdown, that is when there is an increase in the electric field, it causes the velocities of the minority carriers and it breaks the covalent bonds. Again, it is completely accelerated by the electric field. This break will be more relevant through the extreme materials, and also when there is an increase in the high reverse current, this breakdown occurs. In the case of the Zener diagram, the same as like the avalanche breakdown, but there is a difference, that is it happens only in the time of electric field across the diode junction increases. So the force of attraction on the negative charge atoms at the junction, and also this force frees the electrons from the covalent band and moves from the free electrons to conduction band. When the electric field increases, more and more electrons are freed from its covalent bonds. This results in drifting of electrons across the junction and electron-hole recombination occurs. So a net current is developed and it increases rapidly with the increase in the result in the damage of the diode. Since current is only due to drifting of electrons,